Okay, so we're looking at the first page of the Unit P packet. And so we're tackling the Conic Sections component of the review. Right? So for these problems, you can see the examples. Write the equation in standard form, identify the conic, find the necessary points, lines relevant to that conic section, and then graph the conic. Right, you'll see I have my Desmos calculator open here, and for this course, that's typically where we're going to be living. We're going to be living with the Desmos calculator. All right, so what I want to be doing here is first organizing things so that it's completing the square friendly. All right, so I'm going to rewrite. So I'll have 9x squared plus 18x. I'm going to leave a little space so I can complete the square for the x terms. Then plus 5y squared. There is no corresponding y value. We have a 5y squared, but there's nothing with just a y to the first power. So I'm going to leave that alone. There's no square to complete, really. All right. So next step in the process is going to be to add a 36 to both sides of the equation. All right. So I'm going to just add a 36 to the other side. So what I'm going to do here is just complete the square for the x terms. All right. So a little, I don't know if it's a shortcut, but a technique would be that for any expression or trinomial in quadratic form, we could use the model b squared divided by 4a. That's the same as taking the b value, cutting it in half, squaring it, and dividing by the a value. All right, so in this case it would be 18 squared divided by 4 times 9. All right, so it's 18 squared divided by 4 times 9, so divided by 36. All right, so that gives a result of 9. All right, so I'm going to add 9 to both sides. All right, because I'm adding it to complete the square on the left, but I'm also going to add it to the right to keep the equation balanced. All right, so I'm going to factor out a GCF from this, a GCF of 9, which is going to give me x squared plus 2x plus 1 plus 5y squared is equal to 45. All right, so perfect square trinomial factors to x plus 1 squared. We have 5y squared equals 45. Now, if I want to get it into the appropriate standard form for a conic, once you recognize that it's not a circle or a parabola, if it were a circle, the coefficients for the x and y terms would be the same. Or, I'm sorry, the x squared and the y squared terms would be the same. If it were a parabola, only the x term or the y term would be raised to a power of 2. So here it's either going to be an ellipse or a hyperbola. In either event, it really doesn't matter which one it is, the standard form has it equal to 1. So I'm going to divide everything by 45. All right, and that'll allow that to happen. So when I simplify, I'm looking at x plus 1 squared over 5 plus y squared over 9 is equal to 1. All right, so if you match that up with the standard form of an ellipse, all right, so this is an ellipse. Standard form is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. All right, the h and k represent the center of the ellipse. The a and b values, so not a squared and b squared, but a and b represent the horizontal and vertical change from the center, or giving us the length, or it gives us the endpoints for the major and minor axes. All right, so what I'm going to do is I'll get a set of coordinate axes. In terms of the center, we're looking at -1, 0. So I can kind of center this symmetrically. I'm going to plot the center at -1, 0. All right. So just following the model, we know that -h has to be equal to 1, which means that h has to be equal to -1. And k, well, there is no k, so it's got to be 0. So that's our center. All right. The a value is √5. Right, really plus or minus, because if a squared is equal to 5, then a is going to be equal to plus or minus the square root of 5, and b would be equal to plus or minus 3. Since the √5 is associated with the x term, that means we're going to go left and right, so in the direction of x. Since the 3 is associated with the y term, that means we're going to go up and down. So 1, 2, 3, up, because I'm going to plot the up and down because it's just easier. The square root of 5, I don't know what that is precisely. I mean, I could type it in if I want, but I don't want to. The square root of 5, precisely, not really important. We do know that it's going to be between 2 and 3. All right, so I'm going to go a little bit more than 2 to the left and a little bit more than 2 to the right. And then I'm going to draw an ellipse the best I can. I have a little autocorrect on this app, so it helps. And so that's what our ellipse ought to be. So we know it's an ellipse. We wrote it in standard form, the necessary points and lines relevant to that conic. We graphed it, so that's fine. But the points, there are no lines relevant to this conic. There is a major and minor axis, but those are line segments. We wouldn't really need the equations of those things. But in terms of the endpoints, what we call the vertices of the major and minor axes. All right, so I can just kind of pop those in. The longer of the two axes is the major, the shorter is the minor. I'm just cleaning that up a little. I guess it doesn't want to autocorrect into a horizontal line. That's unfortunate. All right, it is what it is. All right, but from the center, it looks like in order to get the two endpoints here, we're increasing the x value by radical 5. So this point would be -1 plus radical 5, comma 0. This point would be -1 minus radical 5, comma 0. Then we're leaving the x value alone, but we're increasing and decreasing the y value. This is a little easier. -1, -3, -1, +3. All right, so those would be the relevant points. Now, there are also other important points in an ellipse. They're known as the foci. All right, if you're actually generating an ellipse from really nothingness, without being given an equation, you would need the foci. All right, two separate focus points of the ellipse. They're along the major axis. We just have to identify where they are. There's shortcuts for determining the location of those, but essentially, it's easy enough to find. There are relationships that allow you to come up with those. But I don't know if this is the most mathematical way of doing it, but I have this little mnemonic. It's the square root of the big denominator minus the little denominator that helps you determine the distance from center to focus. All right, so for an ellipse specifically, so the distance from center to focus so d would be equal to the square root of the big denominator, big denominator minus little denominator. So I say big D minus little d denominator. All right, so in this case, it would be, if you're referencing the two denominators, the square root of 9 minus 5. So the square root of 4, which is 2, plus or minus. All right, so that would be telling me that I'm going up and down 2 units from the center of the ellipse. All right, in which case I'd have a focus point here at -1, 2, and another focus point here at -1, -2, always on the major axis. All right, so then it kind of sort of begs the question, well, how on earth would you know that? You know, like, where's that magical rule coming from? Now, we're all coming from varying degrees of expertise when it comes to pre-calc. So the genesis of this relationship comes from the idea that there is a point on the major axis that has a distance from the vertex along the minor axis equivalent to half the length of the minor axis, right? And that is the location of the focus. All right, so if we know that this value here, we're calling this A, and we know that that other value there has to be an equivalent distance, then we're in pretty good shape. I'm sorry, did I say half the length of the minor axis? I meant half the length of the major axis. All right, so whatever the length is of the major axis, chop that in half. That's going to give you the length of that hypotenuse. All right. There's a lot of stuff going on with these ellipses, so we just got to be careful. So if I'm looking for this distance here, which I'll call D, I'd have this distance here, which I can call B, you know, just to make things as confusing as possible. The reason I'm calling it B is because that's what we called it down here. All right, that vertical change from center was the square root of the denominator. All right, so that tells us that the hypotenuse would have to be B. So in this case, what we could say, and I'll just kind of chuck it off down here below, we would say that A squared plus D squared is equal to B squared. And if you solve, you would get D squared is equal to A squared minus B squared. All right, now if you look at what we did, we took the two denominators and subtracted them. The problem is sometimes you get a positive result and sometimes you get a negative result. If you take the two denominators and subtract them in the wrong order, then you'll get a negative under the radical. So we just kind of forced the issue because the difference is, it's really the absolute difference that we care about. So if we swap the order, we'll get the absolute difference. It's kind of like if you were to say 1 minus 2 versus 2 minus 1. They have the same absolute value, so we just swap the order to get it in the right direction. So another way you could say it would be, if you don't like my big denominator minus little denominator formula, you could say that the distance from center to focus D would be equal to the square root of the absolute value of A squared minus B squared. All right, so any of those relationships will get you where you need to go. It's just there's a lot of stuff going on. Now, do you need to know every aspect of this for the well, that's kind of strange how it's highlighting everything. Oh, I accidentally highlighted the vertical axis. Do you need to know all of this in order to be successful in Calc 3? No. It's just another element of an ellipse that's going to be helpful in order for you to understand what's known as an ellipsoid, which is an ellipse in 3 dimensions. All right, so the more you know about ellipses in 2 dimensions, the better off you're going to be. All right. So all of that mess covers what we need to cover for the concepts of an ellipse, writing it in standard form, check. Oh, actually put the check right there. Identify the conic section, right there. necessary points and lines, that's the big graph. All of this is C and D. All of this stuff. C and D. All right. So that's right into the fire, I guess. Now let's take a look at number 2, which you'll see is a lot easier, but not because of anything other than the coefficients are simpler. Right? So we're looking at 9x squared plus 5y squared in number 1. Here we're just looking at x squared plus y squared. It's going to be a whole lot simpler just simply based off of that information. So let's clean it up. X squared minus 6x, leave a little space to complete the square, plus y squared minus 6y. This time we do have to leave a little space to complete the square, and then move the 18 to the other side through proper equality properties. All right. Use our relationship, our completing the square technique, whatever one you like. I like b squared divided by 4a. All right, so negative 6 squared divided by 4 times 1 is going to be 9, so I'm adding 9 to both sides. It's the same b value for the y term, so it's going to be the same computation, set of computations, so no change there. On the left, or for the left trinomial, we would be looking at x minus 3 squared. The whole point is that if you're completing the square, you're completing the perfect square trinomial. All right? So you should end up with something that factors to a binomial squared. All right? So x minus 3 squared, y minus 3 squared, 36. All right? So this is the standard form of a circle, which is x minus h squared plus y minus k squared is equal to r squared, where h and k is the center. All right, so the center is hk, which in this case would be 3, 3. And the radius is r, in this case would be 6. You could say, well, you know, the square root of a number is plus or minus, but that just implies direction. So you could say it's 6 or negative 6, but all that's saying is that from the center of the circle, you'd be going in both directions 6. So if you're going to the right 6, you'd also go to the left 6. If you're going in the direction of a 45-degree angle, 6 units, then you go in the direction of 225 degrees, 6 units, the opposite direction. All right, that's kind of a different subject for a different page in the packet, so we'll get there. That was strange. I have no excuse for that one. So center at 3, 3. Now, if the center's at 3, 3 and we have to go out 6 units, that's going to put me off the grid. So I can handle this a couple of different ways. One would be to scale my graph. Another thing that I could do would be to kind of shift my axes. So that I have a little bit more room in the positive, or the first quadrant, the positive quadrant. So 3, 3. And then go out 6 units. And then draw a circle. The points kind of trump the diagram itself. So if it's not a perfect fit, that's okay. And honestly, these graph grids are a little iffy in that they're a little bit more rectangular than they are square. So, you know, you might miss a little bit, and that's okay. Worst case scenario, just hide the imperfections with a little bit of makeup, aka make the points a little bit bigger. All right, so we got the center, we got the radius. You don't have to state anything like vertices. because you have a constant radius throughout, not like an ellipse where the distance from center out changes. So, I mean, if you were to list all of the points along the circumference, you'd be at it for the rest of your life. Here, it's 6 units. You know, it's the locus of points equidistant from a single point, so we got what we need. All right, so we've hit 2 out of the 4 conic sections. We hit the ellipse and we hit the circle. So on the next page, or the next pages, we will tackle the parabola and the hyperbola.